Okay, hi guys. So from this video lecture, we'll be starting off with aromatic chemistry. So let me write down the heading first. Aromatic chemistry. Okay. So let's say I have a benzene. Now what happens here is on all the 6 carbon atoms in the benzene ring, they have substituted H groups. Now what happens is we have some electrophile which wants to connect itself with benzene ring via electrophilic substitution reaction. Okay, so what happens is this bond actually breaks up, the double bond actually breaks up to accommodate something, to accommodate electrophile, and positive charge will come on this carbon atom. Okay, and then the Y minus will come into the picture and will take care of H plus, hence again forming a negative charge here, so forming a double bond here. As this carbon atom would have a negative charge because H plus would be removed, hence negative and positive carbon atoms will form bond between themselves. Okay, so we would have something like this. Okay, and E would be added into the aromatic compound. Okay, so this is an example of electrophilic aromatic substitution reaction. Okay, and this, the intermediate, is called either a sigma complex or Wheeler intermediate, and it is also called as rhenium ion. Okay, now the driving force of this reaction is or rather of sigma complex formation is a bond energy of sigma bond and V high temperature. We actually give high temperature for this reaction to take place because it's not easy to break the aromaticity and the double bond between aromaticity of the phenyl ring and double bond between two carbon atoms in the benzene ring. Okay, so high temperature are the two driving force for the forward going of the RDS process, RDS step. Okay, now let us define what is known as a directing influence. So which is actually, as the name suggests, directed by the group which is attached to the phenyl ring. Okay, that would actually determine at which carbon atom would be the electrophile most likely to be attached to the phenyl ring. So this is called directing influence. Okay, so first let us discuss about the groups which are activating and which are deactivating. So activating groups and deactivating groups. Okay, so activating groups will direct the electrophile towards ortho and para position, and deactivating groups will direct the coming electrophile towards meta position. Okay, we'll again classify activating groups into again 3 subcategories as strong, moderate and weak. Similarly, we can also classify or subclassify deactivating groups as strong, moderate, and weak. Okay, so let us discuss about activating groups first. So activating groups which direct the incoming addition of electrophiles towards ortho and para positions. Okay, so let us first talk about strong activating groups. Okay, and these are O minus attached to the benzene, NH2, OH, NHMe, and Me2. Okay, let us discuss about moderately activating groups. And those are this ester group, amide group. Okay, next weakly activating group, so or weak activating, we have CH3 group attached to benzene or phenyl ring, ET, this one or this one. These are all weakly activating groups. Okay, so let's take on some examples here. So we have something like a phenol. So what actually happens when a phenol is attached to a benzene ring? Will have actually negative charge density on when this lone pair of oxygen gets involved in the resonance, we'll have negative charge here. Then this negative charge will again come down to form bond between this carbon atom and this carbon atom. Negative charge will come here again. The same resonating process repeats itself, and negative charge will come here with O plus H here and double bond here. So what we can see that in the resonance hybrid, we can see that partial negative charge is on either ortho positions or meta position. Hence, the incoming electrophile will see more electron density at either ortho position or para position. Hence, it would like to attach itself at these positions. Okay, that's what we mean by that activating groups are ortho and para positioning or directing. Okay, let's see next example. We have something like, again we have something like this, a moderately activating. This was a strongly activating. Now let us see an example of moderately activating. We have again something like this. Now what will happen is, actually why it's moderately activating, because it can either do resonance with itself or within the ether or the ester group, or it can do the resonance with the phenyl ring. Okay, so there is less chance, there is slightly some less chances to have resonance with the phenyl ring, as it is also involved with the resonance with the attached CO group. So hence it is moderately activating, but still it will direct the incoming electrophile to ortho and para positions. Okay, hence this is also ortho and para directing. Okay, let us talk about some more example wherein we have something like this, a phenyl ring substituted with NH and C double bond O CS3, and at the meta position we have CS3 also. Okay, so this from this CS3 the benzene ring will be getting plus H and plus I effects, and from this we'll be getting something like plus M effect majorly. Okay, so as you can see, the electron density because of plus M would be on the ortho and meta positions. This is the ortho, this is the meta position for the amide group. Okay, and for this CS3 as well, this is a weakly activating group, but still it would have direction at ortho and para positions because of its plus I and plus H effects. So it will have negative density at this position and again this position. Okay, so the ortho meta para positions are same for amide and CS3 group. Okay, so with this we come to an end of this lecture, and in the next lecture we'll be seeing deactivating groups. So till then, good luck and goodbye.